Hi everyone and welcome to my YouTube channel. In this video we'll be wrapping up the circles chapter 2 in EGMO book by Evan Chen. Basically in the previous video we discussed the theory part, all the theories we need for this chapter, and in this video we'll be discussing some practical examples. So what are you waiting for? Let's get started. Our first example is from the USAMO 2009 problem 1. So in this problem we're given two circles. They're intersecting at x and y, so xy is the radical axis, and we take two lines, the first line passing through the first center, and it intersects the other circle at 2 points pq, and we have another line that passes through the other center and they intersect the first circle at 2 points as well. They are assuming that P, Q, R, and S, they lie on a circle. They want us to show that the center of this circle lies on the xy, that is the radical axis. Okay, so in order to get started, we need to draw a diagram. And as we do always, we try, first of all, to sketch a quick diagram on our draft before we draw the accurate diagram. So here we just have two circles, something like that. Let's say this one has center O1 here and O2 is there. And then we need to, of course, this is the radical axis. Then we need to take a line here that intersect the circle at 2 points. Those are P and Q. We need to take another line from here that intersect the other circle at 2 points as well, and they're assuming that these points form a cyclic quadrilateral like this. They want us to show that the center of this circle lies on the radical axis, that is this line here. So the center should be somewhere on this line. Okay, so now if we want to draw the accurate diagram, as you can see, we have actually one challenge here. First of all, we can draw the two circles easily, take their centers, draw the two lines PQ and RS. However, they are putting an assumption that is PQ, R, and S. They are assuming they lie on a circle. How exactly can we enforce this on our diagram? Because otherwise we will not have like a good diagram. As you can see here, it seems that the center of this circle, that is if we even have a circle, doesn't lie on the xy, that is the radical axis. So we need to try to find a way to enforce this condition. Usually this is a challenge in these questions in which they suddenly assume something. Okay, so let's try to think, how can we enforce this condition? We need to have a third circle such that like we have these two lines intersecting the circles, the two circles, they lie on this circle. Well, if you try to think about it, this diagram should be familiar to you. We already in our previous video discussed one very important theory about this exact diagram. If you remember, we said that given like these 2 points here and another 2 points here, we know these lie on a circle if and only if they lie their intersection, that is this point here, if it lies on the radical axis. So if this point lies on the radical axis, then clearly they are going to be cyclic. So this is exactly what we should be doing. Like keeping that in mind, now we can draw an accurate diagram by simply forcing this point. So now, for example, if we choose this point here first on the radical axis, then we're going just to connect from the center to this point. We're going to connect this and connect this, and now we'll get 100% like a circle. And of course that means that we're going eventually to have the center lying on xy. Okay, so now this is our plan, how we're going to draw an accurate diagram. So let's now get rid of this, and like simply bring our accurate diagram. Okay, so here we go. Here I just draw the two circles as I told you. These are the centers O1 and O2. And then I picked a point on the radical axis. The radical axis is this xy. This is our point, like h on the radical axis. What I did simply, I took O1h and join it to get P and Q, and I took also O2h and join it, and I got R and S. And now, after I did that, of course, now we must, like, this thing is cyclic for sure. So I just draw the circle, and indeed, I found that O3, the center, lies on the line xy, that's the radical axis. Okay, so the first challenge, we're done with that. We have now our accurate diagram. Okay, now let's think about the question. How can we show that O3 lies on xy? Of course, if you remember, we shouldn't be doing like this. We should always make this line dotted so that we don't get tricked and like think that these are already lie on their collinear xy and O3 and get a circular proof. Okay, now let's try to think about our question. What do we have here? We have three circles. We have like three centers as well. And we have like radical axis, that is xy, for these two circles. And of course we have like these 4 points as well. So how exactly can we show O3 lies on xy? Well, if you look at this diagram, you actually not just have a single xy that is the radical axis. We actually also have two other radical axes as well. And so, if we try to think, what do we know about radical axes? What properties do we know? Like the literal definition of radical axis, we know it's the set of points having the same power of point. Okay, that here doesn't seem like that much helpful here. What other properties do we know about the radical axis? Well, remember, the main result we got about radical axis, we know it's a line, and this line is perpendicular to the line joining the centers. Well, guess what? Here we just have three centers, O1, O2, and O3, and we have three radical axes. So definitely we should be joining the all the lines joining the centers. So for sure we should go ahead and draw this O1, O2. We should do the same for O3, O1, and we should do the same for O3, O2. And now, what we know that this thing is the radical axis here. Sorry, this thing like SR is the radical axis. So O1, O3 is perpendicular. So we have here 90 degrees perpendicularity. We also have the same thing here. O3, O2 is perpendicular to PQ. And we know actually that XY is perpendicular to O1, O2. Be careful, however. We know that XY is perpendicular to O1, O2. We don't know O3 lies on that line yet, so be careful. So right now, if you look at this, well, clearly now you should be observing something very interesting. If you look at the triangle O3, O1, O2, we just have here 90 degrees and 90 degrees and 90 degrees. So we have three altitudes actually in this triangle. This one is an altitude. This thing is another altitude. This thing, we don't know it's an altitude yet because O3 is not necessarily on the line. In fact, if we can show that O3 and XY, this thing is an altitude, then we're done. So here actually, this thing is already easy to see because point H, the definition of point H, which is the intersection of O1Q with O2S, which we already proved using our theorem that we discussed in the previous video, that actually it lies on the xy, which is the radical axis. So we already know that H is the orthocenter of this triangle. So that means the line O3H, it should be perpendicular to O1, O2. However, we already know that the line HX is perpendicular to O1, O2. So that just proves that O3, X, H, and Y, they're all collinear. And that actually finished the problem because we just showed that O3 lies on the radical axis. And yeah, that's it. We're done. Actually, we're not. And here we have like a very poisonous trap here. And this trap, if you try to think about it, like regarding the orthocenter and these kinds of stuff, everything seems logical. So where exactly is the trap? Well, the main idea was our definition for point H. Here, for point H, we defined it with the intersection of O2, like basically line RS and the line PQ. And we apply just the theorem that we knew. We know that if we have these guys are cyclic, they line us on a circle, then we automatically know that this point lies on the radical axis. However, if you recall, that theorem wasn't actually this. It has a special case. The statement of that theorem, in which we mentioned it, we said that given that these 4 points lie on a circle with center O3 that is not on that's not collinear with O1, O2, then yes, the intersection of basically the two lines that are PQ and RS, which is point H, it lies on the radical axis. So that means that if O3 lies on this line here, if it lies here, then we cannot apply our theorem. Why exactly? Because point H will not even exist. Because we mentioned that in this point, in this case actually, the 3 circles don't have a radical center, as the 3 radical axes will be parallel. Again, if you're not understanding what's happening here, refer to the previous video in which we discussed this very important theorem. So that means here we need to discuss another case, another diagram in which point O3 lies on the line O1, O2, and in which we know that RS and PQ and the radical axis XY, they are all parallel. So here is the diagram for the other case. As you can see here, I just have the circle, the first circle omega 1, the green circle with center O1, and then we have the other circle, that's omega 2, the blue one with center O2, and then we take O1 and take the line PQ, and as we said, this case, the radical axis XY, we're going to have the other 2 lines that are like PQ and RS, they're going to be parallel to XY. So here we have the parallelity actually for these. Okay, this is one thing. And then of course we're going to have P, R, S, and Q. This is going to be cyclic, and this circle is going to have a center O1. Remember that we already know that in this case O1 and O2 are all collinear. So here basically O is actually O3, but let's just call it O for now. And our goal is to show that it lies on XY, basically. So this thing is actually like the O3 right now, and as we said, we're going just to show that it lies on the radical axis XY. Again, be careful, because we don't know it lies yet. Alright, so how exactly are we going now to approach that? As you can see now, we have another diagram. We cannot apply the same techniques, of course, but we have actually many information here. For example, if you just look at these radical axes, PQ is the radical axis still for the 2 circles, and the RS as well, between omega 1 and the third circle, omega 3, let's call it. So we already have the perpendicularity still holds. Like if we have these 3 centers, we already know this thing is perpendicular and this is perpendicular. So we already have lots of 90 degrees. And remember, we already know that XY actually is parallel to PQ and RS. So that just means that line XY is also perpendicular over O1, O2. So we should have a perpendicularity here. However, we cannot say that because we don't know that O3 lies on that line. So if I do something like this, you will think that O3 x O1 is 90 degrees, but we don't know that actually. So to get rid of this, because it's really going to be confusing, why don't we do a phantom point here? What does that mean exactly? It means actually, instead of defining O3 to be the center of the circle, like of the circle P, R, S, and Q, instead of doing that, let's do the opposite. Let's actually define like O or O3, the same. Let's define it to P to be like the intersection between O1, O2 with XY. Why are we doing this? Because now we already know we have a 90 degrees here, and we know exactly where is this point O. We know it lies on XY. We know we have this nice perpendicularity. So we have more control of this. But of course now we don't know it's the center. Our goal is to show that it's the center for P, R, S, and Q. So now basically what is our mission right now? It's simple. We just need to show that OP equals OR equals OQ equals OS. Alright, so let's proceed with doing that. Well, the first thing you can actually see is that if you look at OP and OQ, this we already know they are equal. The reason is simple. What is the perpendicular bisector of the line PQ, of this line? Well, we already know O1 is the midpoint of it. So we know that this thing actually is the perpendicular bisector for it. The reason actually is simple. You have point O2 is the center for the blue circle. P and Q are on the blue circle. So if you take from O2 perpendicular to line PQ, you're going to end up like with O1 being the midpoint of PQ. So that just means that this thing is the perpendicular bisector. The same thing goes here. So that means we already know that OP equals OQ, and we already know that OR equals OS. So now our only goal is just to show that OP equals OR. So let's actually erase these, forget about point Q and S, and let's just focus above on OP and OR. How exactly are we going to show that OP equals OR? Alright, how exactly can we do that? You can think about this and have many ideas. Maybe, since we have here an isosceles triangle, our goal is to get an isosceles triangle. Maybe you should try some angle tracing to get maybe these angles are equal. However, this seems a little challenging here, as there is not much you can do, or at least what I can see here. I don't think there is much we can do for angles. Instead, actually, we have a very nice idea here. Because we have like tons of 90 degrees, this is like a rule of thumb when you have tons of 90 degrees like that, probably applying Pythagoras is a good idea. So instead of trying to do angle tracing, let's try to go, like instead of angle tracing, let's do length tracing. So right now, we're going to change our goal into showing, finding OP using lengths, and finding OR also using some lengths. And of course, our main tool will be Pythagoras here because of the 90 degrees. Okay, so let's start. How exactly can we find OP? Okay, taking a look at it, well, the only way that seems logical is to apply Pythagoras here. So let's go ahead and start our length tracing journey. So OP square is equal to O1 square plus O1 P square. Okay, now we broke that into O1 and O1P. Clearly this is not enough, because if we do it from the other way, like also OR square, if we apply this like the same technique, we're going to get its O2 squared plus O2R square. Clearly we don't have something like cancel from here or there, so we need to proceed. We need to do it further. Okay, what exactly can we do here? Let's think. So now we have O1 and we have PO1. What can we do here? Well, one idea might be for O1 to try to break it further. We might, for example, do something like this. If we look at this triangle here, now we have O1. We can apply Pythagoras on this triangle and get rid of O1 into something like O1x and XO. Is this better or worse? Let's see. So now, if we do that, we're going to have OP squared is equal to XO1 squared minus XO squared plus O1P squared. Let's see. What is XO1? XO1, if you look at it, X lies on the two circles, right? And because O1 is the center of the green circle, so this thing is actually R1, right? So this thing actually is just R1, which is the radius for circle omega 1. Okay, so this thing is R1. This seems nice. What about XO? XO, here if you look at it, it's actually half of the distance XY, as you can see. So if you think about it, when you do it when we do the same for OR, it's going to repeat again. We will also get XO. So this thing is already like very cool because it's going to cancel. So we can actually like totally forget about that, and now just like worry about R1 and O1P. Okay. So right now we need to worry about R1 squared plus O1P squared. How can we proceed with this one? How can we proceed with this O1P? Is there anything we can apply here? Well, how can we find OP? If you look at it, we need to also try to search for some right triangle here that has it. And clearly there is a very easy one. Of course, like you will not repeat, like go back again. You should not use this, otherwise you're going in a circle. So you should just like be picking the other one, which is this. If you do it right now, O1P squared, we can actually write it as PO2 squared. So let's actually just do that. This thing is now R1 squared plus PO2 squared minus O1 O2. Okay, now if you look at this thing is very nice. O1 O2 is going to repeat the same, like it will appear again for OR as well. PO2, what is PO2? Let's look at PO2. O2 is the center of the circle omega 2. P is a point on the circle omega 2. Alright, very nice. So that's actually just R2. And now, indeed, like everything is nice because this thing actually that appeared here is R1 squared plus R2 squared. So it's going to also appear as R2 squared plus R1 squared for the other one. O1, O2 is going for sure to appear for the other one as well. And as we said, XO is going to appear there again as well. So right now, of course, you're doing all of that on your draft. Now, the real calculation, you're just going to apply a bunch of Pythagoras and go immediately like that. So you'll say OP squared is equal to O01 squared plus O1P squared, which is equal to, you'll go and break OP. Let's break, I mean the first one, O01 squared, is just going to be XO1 squared minus XO squared. And we're going to also break O1P. How did we break O1P? We just said it's PO2 squared minus O1 O2 squared. And now you'll just tell them that XO1 is actually just R1 squared. So this thing is R1 squared. And PO2 is just R2 squared. So it's plus R2 squared. XO is, as we said, it's going to appear again for both of them. So let's keep it. And then O1, O2, it's going to appear for both of them. So yeah, that's it. You can just do the same here. And then, of course, you can do the same for OR. Okay, I'm not going to do it. But say you will just like get the same thing here. All of these guys again. And yeah, that's it. We're done. So that just shows that OP equals OR equals OQ equals OS. And hence O that lies on XY. Our new O, by the way, this strategy is called a phantom point because it's not the same as the original O they define. But we proved that actually now it's the same. So now our new O, our phantom point, as usually like they call it O3 prime, because it's not O3, it's an edited version of O3. It's actually the same as O3, and hence we're done. So again here, the main idea was, we just like here, first of all, applied our theorem to handle this cyclic issue. get our point H lies on the radical axis, and then we just apply the simplest property of the radical axis, that is the perpendicularity that we get, and we just notice it's an orthocenter. However, the main poisonous trap that we should always be careful when we apply this theorem is that you need to consider the case that H doesn't exist. What does it mean? It means that these guys are parallel, and that happens when O3 lies on O1, O2. And in that case, we just proceeded with a length tracing proof. Alright, so we're done with this problem. Let's move on to our next example. Our second example is the very famous Euler's theorem. So this theorem states that if you have just a triangle ABC, and you know, like big R, capital R and small r, they are just the radius and in radius, the circumradius and the in radius of the triangle, and O and I are the circumcenter and incenter, then we can actually calculate OI. The length of OI squared is just equal to R times R minus 2R. And there's actually a very famous inequality that's called Euler's inequality, and that is capital R is greater than or equal to 2 times R. This inequality is really not important when you're solving geometric inequalities. So sometimes you might have like capital R involved, and you want like to move it to small r. So you can just use that this fact, R is greater than 2R. And of course the proof for this comes actually from the Euler theorem itself, as this thing here, it's a positive thing because it cannot be negative. If it's negative, then the length will be negative. So we have, of course, that it must be positive. Anyway, let's try to work with this question. So to work with this question, as you can see, we don't really need to do anything, just like some simple diagram, just a triangle ABC, a circumcircle with center O, and an incircle with center I. And we just need to calculate this thing, OI square. And we need to like find it using this relation. Okay, so how can we get started with such a question? The first thing, as we said, the main goal is to find OI squared. Well, how exactly can we find OI squared? Is there like a Pythagoras here, maybe, or some other technique to try to find this OI squared? Well, it seems that we don't have any idea how to find this thing, as like it's really like there is nothing we can do. No Pythagoras, nothing that much helpful here. So instead of thinking about OI, we should probably look at our equation here. As you can see here, if you look at both sides and try to expand this here, it's R squared minus 2R times capital R. Okay, now if you look at this, you might be recalling something nice. R squared, OI squared. This thing here seems like power of points, right? Remember the power of points? We know that power of point P, generally speaking, it's equal to PO squared minus R squared. Guess what? We have R squared and we have something O squared. So this seems very nice. So let's just move that thing here and move that thing there and try to form this into power of point. So if you just rearrange, we're going to have here 2 small r, capital R, it's equal to R squared, capital R squared, minus OI squared. And this thing, what does it represent? It represents the, actually not power of point, but the negative power of point. But who cares, because if you remember, like we just look at the absolute value. So we just need to show that the absolute value of power of point I, it's equal to 2R small r times capital R. Okay, now this seems more reasonable. We can now do more things to this, because now we just need to work with power of point I. So we need to work with power of point I with respect, of course, to the circumcircle. And this seems way nicer than working with OI, which was like really ugly and not approachable at all. So now we can try to think about power of point I. But still, how can we exactly deal with power of point I? Remember, what do we know about power of points? We know the original definition comes from this thing here, but we escaped from this, so of course we will not return to it. So we should be trying the other things, like if you have like something like this, you multiply like this times this, right? So we should be probably trying to use something like that. But of course we will not be taking 2 random points on the circle. Instead, we should be using our own points. They are already in the diagram. So for example, we can pick point A. Of course, you can pick B or C, but let's just pick point A as it's all symmetric here. So basically, in order to represent the power of point I, we just need to draw AI and intersect this here. Let's say point L. So now we can transform our question into this. 2 small r times capital R is equal to AI times IL. This is what we are looking for now, our goal. Okay, now this thing is way more approachable, as you can see. In fact, right now you should have observed something. If you didn't, then you haven't watched the first lesson, which is about the first chapter. Because this point L, we already really love this point. In fact, we called it the golden point, if you remember, back then. This point L is just the midpoint of the arc BC, right? If we recall, what are the properties about this point, this golden point L? We know, first of all, it lies on the, it's basically the midpoint of the arc BC, as it actually lies on the angle bisector AI. We know, of course, that this triangle is isosceles, so it lies actually on the perpendicular bisector here as well. And in fact, we know that it's which is the most important property, it's actually the circumcircle of this triangle BIC. And in fact, if you recall, if you extend this thing here, it's going to give you IA, which is the AX center. So remember that L is the center of this circle, which means that IL actually is the same as LB, which is the same as LC. So keep in mind that we can play on this. We can manipulate IL to anything we want. All right. So what can we do right now? How can we prove this thing? So as you can see here, we have a bunch of stuff, 2 times R, small r, and capital R. We also have AI and we have IL. As we mentioned, IL can be manipulated to BL or CL. That's not a big problem. But how exactly can we prove something like this? How can we link AI, IL, R, and capital R and small r? Well, clearly, the first thing we need to do is we need to visualize these guys here, like the small r and capital R, as they don't appear on our diagram yet. So we need to visualize these. So in order to visualize small r, we can simply just drop here something, drop a projection here. For example, can drop this thing here. Okay, you might tell me why I didn't drop it, for example, here. Well, the idea is simple. Remember, I want to work with AI. So probably if I drop something like this, it's going to be better than dropping that, because now I have like a nice right triangle that has R here and that has AI here. So this thing is really cool. Let's work with this one, this point here. Let's name it something like D, for example. Okay, so now we've visualized AI, like small r. IL is already visualized. We can in fact manipulate it to BL or CL. The only problem is with R. But in fact, remember that we have the 2 as well. So how to visualize 2R? Probably we need to have some diameter, right? Something like that. Okay, where exactly should we draw it? Okay, in order to think about that, first of all, how exactly are we going to get this relation? Let's think about it. How do we usually get relations like this, like in geometry, AB equals CD? Well, usually the ideas that we can do is maybe power of points. But remember, we already escaped from power of point. We're escaping from power of points so far. So we don't want to use power of point here, as there is really not that much clear approach here to keep going with power of points. So the other idea is simple. Similarity, right? You can just write something like this and they get a ratio, and then hope that you have some similar triangles. So this idea is really cool. So let's try to think about it here. Let's see. So we have this small r and we have the AI. So if you think about it like this, R over AI, you need to show it's equal to IL over 2R. So now we have R, small r over AI. So probably we should be looking at this triangle here, this right triangle. Maybe if we can show we have another triangle that is similar to it and that has these as sides, IL and 2R, then we'll be done. So let's think, how can we construct a right triangle that has 2r in it and that has like this length, IL. Remember, if you have IL, BL, or CL, that's fine. We can, as we said, manipulate on that. So now we just need to think, how do we draw the diameter? Well, one of the easiest ideas here is simply to connect O to maybe L. Remember, all of them like are attached to L, whether you want to use IL, BL, or CL. So eventually, joining this is a good idea. Let's name this point something like E maybe. And now you know that this thing is a diameter. So, like in fact, if you pick anything, like this, for example, you're going to get a 90 degrees because it's a diameter. So you already are getting what we want, actually. This thing is 90 degrees. It has a diameter 2r, but does it have IL? It doesn't have IL here as a length. So maybe like we should draw another point. So instead of drawing it from A, maybe if we draw, don't know, maybe like from B. If you draw it from B, now you have the 90 degrees here. Now we still have the 2R, and the IL we have instead BL. As we said, BL is equal to IL. So yeah, finally we got our like triangle. These two triangles are, both of them, they are right triangles. We just need to show similarity. To show similarity, we need just to have another angle, and of course to do that is actually very simple. Look at this angle here. This angle corresponds to this arc. So it's actually the same as this because it also corresponds to this arc as well. So indeed, from this similarity, we simply are done, because now we just like write the similarity ratio, and we just get this thing here. The 2r is EL, the IL is BL, the R is ID, and the AI is already AI. And yeah, that's it. Basically, we're done. So again, the moral here of this question, first of all, we don't really have a clear method to calculate OI square. So we just try to play with this equation here. And like when we expanded this, we immediately noticed that we have R square, OI square. So we immediately thought about power of point, because this is the thing that is like the formula of power of point. So in fact, we just did that, and we discovered that this thing is power of point I. And to play with power of point I, we just need to have a chord that has I in it, and we just draw a chord through A. So we got this thing here. Now we thought, how can we get this? Well, this seems like the only idea that came to our mind is to try to get some similarity here. If we get a similarity, then you're going to get something like that, AB equals CD. And to do that, we just looked for the right thing. What should we construct? We construct everything logically, and yeah, that's it. That was the idea. Alright, so that was our example 2, and now let's move on to our example 3. Alright, our example 3 for today is from Russian Olympiad 2010. So let's give that a try. We've got a triangle ABC with perimeter 4. So they are giving us the perimeter of our triangle. Then they are defining 2 points, x and y, on rays AB and AC, such that AX equals AY equals 1. Okay, so they're defining everything numerically here, it seems. Then we're given that segments BC and XY, they meet at a point M. Alright, what we need to prove is the perimeter of either ABM, triangle ABM, or ACM is 2. So clearly that means it's going to depend on our diagram. One of these two triangles will have perimeter 2. Okay. So let's get started with this question. So the diagram is going to be something like this. We have a simple triangle, and then like they're defining x and y such that let's say like y is here, maybe here, AY is 1, and x is here such that AX is 1 as well. And then we're just intersecting this thing here. This is M, and we need to work for this. Either this triangle ABM or this triangle ACM is going to have perimeter 2. Okay, how do we, first of all, start with such a question? Of course, the first thing you need to do is to draw a good diagram. To draw a good diagram here, because they're defining everything using like numerically basically, so let's just do it numerically. It's very easy. So first of all, we want to have a triangle with perimeter 4. You can just pick some sides, like some side lengths. If you are feeling that like first you don't want to draw 4 centimeters, you want like to the diagram to be bigger, then you can like scale it with whatever factor you want. You can multiply by 2, by 5, whatever you want. You can even multiply by 10. So for example, if you multiply everything by 10, like the parameter is 40, ax, ay will be 10, and this here is going to become 20. And let's say, for example, using your ruler, of course you need to pick sides first. Let's say you pick something like maybe 20, 15, and 5. So now if you draw this like as 5, this thing as 15, and this thing as 20 using your ruler, then you got yourself like your triangle. Of course, like in order to draw such a triangle, it's easy to do a construction here. First of all, draw the 20, then take your compass and draw here a circle with 5, and then draw here a circle with 15. Wait, I think this in particular doesn't work, because guess what? Okay, it's good that we have fallen in this trap. So that, I'd like to warn you about this, because you need to actually make sure that your triangle satisfies the triangle inequality. Because look here, 20, 5, and 15, if you add these, you're going to get this. But we know from the triangle inequality, this is going to be greater than this. So actually this, like what I choose here, is bad. And you can easily like fix it by just reducing this a little, maybe like 18 here. Maybe like making here 16 maybe, and 6. So now it works. Okay, anyway, again, so that you draw first of all this 18 thing here, and then you take the circle that has radius 6, like this, and then you take another circle that has radius 16, center it here, and you draw it, and of course the intersection points will be will form you with your triangle. Alright, so this way we can just draw like a nice diagram, and then we just like can continue. So the diagram is not that issue here. So I'm going to immediately assume that we have the diagram. I'm going to bring it here. Okay, here we go. So this is our diagram now. We have a triangle ABC with perimeter 4, and we have AY equals AX equals 1, and we need to show that either ABM or ACM is going to have perimeter 2. Okay, so the first step, clearly, in order to start with such a question, we need to know which triangle we need to prove it has parameter 2. Is it ABM or is it ACM? Okay, it's easy actually to decide. Like if you say this thing is actually has parameter 2, we already know that this thing here is 1. So that will mean that this plus this plus this is going to be 1, which is clearly incorrect. And the proof is actually simple. We already know that this length, the whole blue thing, it's actually greater than AY, because like as you know, it's actually the same as the triangle inequality. But let's say you just like want to move from point A to point Y. The shortest way is to go AY, right? A straight line. However, if you go A to M to C to Y, then this is longer, so that means it's greater than 1. So that just means in total that this thing has parameter greater than 2. So that doesn't work. So we should like just work here ABM. Okay, so that means according to this diagram, we need to work with our triangle ABM. Of course, like the whole thing depends on our like diagram. Anyway, right now we want to work here with the triangle ABM to show that it has parameter 2. By the way, let me know in the comments what is the condition that what's the condition that like based on it we have either AMC or ABM. It's going to be parameter 2. Okay, right now here in our diagram clearly it's ABM. So let's now work with ABM here. Okay, so we need to show AB plus BM plus AM is equal to 2. But the problem is in this question, it's really weird question. Like see, everything is defined using numbers. We're not used to that. Usually like the problem, the geometry math Olympiad problem, is defined using like some stuff, like we drop an altitude, we intersect circles, we do something. Like we don't just say that ax equals 1, ay equals 1. So how can we handle that? We need to escape from numbers to things that are better. We want to work with point x and y. We need to know what is point x, what is point y. We don't just want to be working with lengths. Okay, so this is like our main challenge here. How can we visualize everything and get rid of numbers? Okay, let's think about that. First of all, we know that the perimeter of a triangle ABC, it's 4. Well, we have a perimeter. How can we visualize the perimeter? Do we know any idea how to visualize the perimeter? Try to think. Well, if you remember, like usually we deal with something that is semi-perimeter, right? This thing comes a lot, and this thing is visualized actually using the ideas we discussed in our like previous video. We know right now that is the semi-perimeter. It's 4 over 2, so it's 2. Okay, we know it's 2. Because we're trying to visualize to get rid of numbers, that means if we visualize S, it's going to help us here. How can we visualize S? Do we have something that has length S in it? Well, yes, we have. If you remember, if we have a triangle and we draw the x circle, then we're going to get some lengths that have S on them. So that immediately suggests that we draw here the x circle, the ax circle. So let's just do that. So I'm just going to extend this thing here. And extend this thing here. And let's say, okay, this is not going to be accurate, but something like this. Of course, this is a very bad circle. But anyway, our goal is just to visualize. So this thing is IA. And now we have this point here, the contact points here and here. Let's call these something like Q, V, T. Now, we know that if we drop just the perpendiculars or projections from IA to these, all of these are, of course, 90s. And they're all equal, of course. They are RA, in fact. And how exactly S appears here? Well, it's just the length of this thing, AU. AU is S, which is 2. AV is S, which is 2. Okay, so now we handled the perimeter thing. But what about X and Y? They told us that AX equals 1, AY equals 1. Well, wait a minute. Now we have AU is 2. That means X is the midpoint of AU. Y is the midpoint of AV. So guess what? We just got rid of the numbers that are related to X and Y. So now we just got rid of all the numbers, but we still have to deal with this. We need to show that the perimeter of ABM is 2. So let's see, what do we need to show now? AB plus BM plus AM is equal to 2. How do we get rid of the numbers here as well? Well, remember, we know that AU is 2. So that means we need just to show that these add up to AU. Okay, so now this is very nice. We got rid of all the numbers, which is exactly what we wanted, using our visualization. So now we want to show that AB plus BM plus AM is equal to AU. Well, if you look at it, AB is already there in both of them, so we can delete AB. And now instead of working with AU, we just need to work with BU. So now we just need to show that BU is equal to, BU is going to be equal to BM plus AM. Let's have a look at this. If you take a look, what is BU? BU is a tangent, right? BU is a tangent to the X circle. It's in fact equal to BT. This is equal to this. So again, if you move this to BT, if you delete this and made it BT, now we can delete BM as well. So I'm going to delete Vm, and now it's going to become empty. Alright, so now we just need to show that Am equals empty. So guess what? It turns out that we just need to show that Am equals empty. This is exactly the question asking. Okay, so how can we show now that Ma equals empty? Okay, if you look at it, we know that empty is a tangent. So we know like empty maybe is equal to something like this if you draw another tangent. But that doesn't seem that much helpful here. So how can we deal with this exactly? Let's recap our question. We're given triangle ABC, the x circle, the AX circle, the tangency points U, V, and T, and like from these midpoints, which are, let's visualize that. From these midpoints, we draw line XY, and it intersects BC at point M. And our goal is to show that MA equals MT. Alright, how exactly can we show MA equals MT? Well, if you look at this diagram right now, and because MT is a tangent of this circle, you might be thinking about something like MT is the tangent. So by power of point, we know that MT squared is the power of point M with respect to the AX circle, right? But the problem is, if you look at MA squared, it really doesn't have like any circle there. So like if you were trying to say that power of point M with respect to this circle is equal to power of point M with respect to some other circle, that is showing like M point lies on the radical axis of two circles. That seems a good idea, but at the same time, we don't have another circle. We want to have another circle that has like that is here. That, like for example, let's say something like this, maybe. If we have something like this, then we just need to show that M lies on the radical axis between these two circles, the AX circle and this circle here. However, what exactly is this circle? We need, as we said, a circle like that passes through A, and that has maybe like this thing is kind of a tangent, so that this thing is MA squared is the power of point. However, like it's really like we don't have that much here actually. We can think about what circles can we think about right now that pass through A. We don't have really any circle in mind right now. So what should we try to do? Well, actually, if you've been following the previous video, we discussed this exact diagram. This like exact diagram should be familiar to you. Remember, we draw a circle. Oops. And we have a point here, and we have tangent, another tangent, a midpoint, and another midpoint. And this line actually is pretty famous line. If we have like point A here and this circle, something like gamma, then this line represents the radical axis between this circle and the circle centered at A with radius 0. So yeah, this point is actually a circle. Again, if you're not grasping that, then make sure you have watched the previous video as we discussed that in details. So that means right now, if you look at this exact diagram, which is really the same as this, we will easily see that line XY is the radical axis between the AX circle and the circle with radius 0 at A. So that means since M lies on that line, then we automatically know that the power of point M with respect to this circle, that is MT squared, is the same as the power of point M with respect to this circle here with radius 0 at A. So that means the power of point, of course, here is just MA squared. So indeed, we got MT squared equals MA squared, and that means MA equals MT, and that means we are done. All right, let's recap. So for this question, first of all, we draw the diagram using the lengths they gave us. But then we quickly wanted to get rid of these lengths because they are ugly, and we want to kind of visualize these lengths and get rid of them. So to get rid of these numbers, we thought a little, how can we visualize the perimeter? And we remember that we know how to visualize S, so that was easy for us. We just take the AX circle, and you know these guys here have length X. Then we immediately notice that AX equals 1. That just means X is the midpoint of AU. Same thing for Y is the midpoint of AV. So we got rid of those length conditions here. The remaining thing is only for 2. To get rid of 2, we just noticed that AU is 2. So we just need to show that AB plus BM plus AM equals AU. And thus began our journey to get rid of these lengths step by step. First of all, we got rid of this easily. Then we got rid of BM by manipulating BU into BT. And then we just ended up with this task showing AM equals MT. To show this, we thought about, since MT is like the tangent here, so MT square is the power of point with this circle. However, the problem was with point A, we don't have like really a clear circle. However, when we looked at our diagram, and remember this, which is like really important figure, you should keep in your mind. It appears a lot in Math Olympiad problems. We immediately remembered that we can use a circle with radius 0. And that immediately killed the question. Alright, with that done, we're going to be moving forward with another example. Alright, we're done actually with the examples in the book. So let's just go over the problems. Of course, we will not be solving all of them. But let's just scroll here and talk a little about some of them. Okay, this one here is easy. Make sure you solve it on your own. For this theorem, actually, the Pitot theorem, is really very famous and very important to keep in mind. It's a technique to handle quadrilaterals that have an incircle. So, for example, as you can see here, ABCD is a quadrilateral, a random one. They are telling us that there is a circle inscribed in it. If we know this, then automatically we know that AB plus CD is equal to BC plus AD. So the sum of opposite sides they are basically equal. And in fact, also we can use it in reverse. So we also know that if AB plus CD is equal to BC plus AD, then that means it has a circle that's inscribed in it. So keep that in mind. This is very important. Always remember Pitot theorem to handle something like that. In fact, there is another technique to handle these questions in which they ask you prove that there is an incircle passing through. And the idea is very simple. What exactly is the center of such circle? So the center of this circle, try to think about it. Since this point here is equidistant to this line, this line, this line, and this line, then it lies on the angle bisector, right, of all of them. It's equidistant to this and this, so it automatically lies on the angle bisector here. Same thing for here, here, and there. So that means if a quadrilateral has an incircle, then automatically we know that all the four actually angle bisectors meet at one point. That is the center. So maybe you can also use this instead of Pitot in some other questions. Keep that in mind. All right, moving here. Okay, these questions are not that difficult. They're all good exercises on the chapter, of course. This question is about moving points. Here I just want to give you just one piece of advice generally for these kinds of problems. Whenever having a moving point question, what do I mean by that? I mean just look here, for example, what they are telling us. Prove that no matter where one chooses the point M along this segment, all the lines will pass through some fixed point. So this is what I call here a moving point. They are moving the point M, and when they are moving the point M, the line MN is changing, of course, but it's going to always we need to prove that it's always going to pass through some fixed point. So how do we solve these types of questions? Well, actually, there is a very famous and very important and useful technique. That is, try to pick the extreme cases. Not actually just extreme, just special cases in general. So some actually cases sometimes are really easy to handle. For example, maybe like if you take the midpoint of the segment AB, you will easily actually see that this thing is very like easy to handle. And maybe if you actually take point M to be point A itself or point B itself, you will also going to get some nice stuff. And that means you will get, like for example right now, 3 segments or 3 lines. You'll automatically know what exactly is this point K that you need to work with. Now that you figured out what is this point K, you're doing all of that on your draft, of course. Now you know what's your point K. So now you just show that this point K that you already know passes through any line Mn in general. So keep this idea because it's very famous when solving these questions. Questions about locus or moving points. Okay, let's move on. All right, these are all like nice problems, not that hard. They're all just on the chapter. Okay. Yeah, I'm not going to spoil anything for you. You can do this as a practice. Let me see. We have some observations here. Yeah, all right. No more stuff. But we'll be just be solving like this particular question because it has like a unique idea here. So let's just solve this problem, and we'll be wrapping up the video. Okay, so I'm going to take that and take the diagram as well. Right, our last example for today is a problem from Canada, 2007, problem 5. So the question is asking us to just simply draw a triangle ABC and take the incircle and take the contact triangle DEF, and then omega is the circumcircle ABC, and then they're giving us 3 circles, omega 1, 2, and 3, that are AEF, BDF, and CDE, the circumcircles of these 3 triangles. And they're telling us that omega and omega 1 intersect at A and B. So they're defining point P as the second intersection between omega and omega 1. Similarly, they're defining Q and R. We have 2 parts here. Part A, prove omega 1, omega 2, and omega 3 intersect at a point. And part B, we need to show that the 3 lines PD, QE, and RF are concurrent. Okay, so it's very easy to draw this diagram. So I'll immediately take the diagram as like there is nothing interesting here in this diagram. We can easily draw it. So as you can see here, triangle ABC, and we have the incenter as I, and we simply just draw the incircle and the contact triangle D, E, and F. This is D here, E, and F, and then I just took the 3 circumcircles of the triangle AEF and the other ones, as you can see. So let me actually write these because they are too small. E and F. This one here is P, this one here is Q, and this one here is R. The intersection of these circles with the original circumcircle. Okay, part A is telling us prove that omega 1, omega 2, omega 3 intersect at a point. Well, looking at this diagram, it's like a piece of cake. Clearly, they all intersect at I, right? And the proof is actually also a piece of cake, very easy. Like we just need to show that point I lies on the 3 circles. So how can we show that point I lies on this circle, omega 1, let's say? We just need to show that A, F, I, and E, like this thing is cyclic, this quadrilateral is cyclic, which is really easy. Just like draw this thing here, We already know that this is 90, right? And this is 90. So in fact, this actually, omega 1 is the circle with the diameter AI, right? The diameter of this is AI. This one is BI, and this one is CI. So yeah, point I definitely is the common point between these 3 circles. Okay, so we're done with part A. It's very easy. However, the real challenge is with part B. Part B, we need to show that oops, I deleted the points. We need to show that the 3 lines, the first line is PD, the other one, similarly, QE and RF. They are concurrent at a point. Okay. How can we exactly deal with such a question? This is, of course, a concurrency problem. We need to show three lines are concurrent. How exactly do we deal with concurrency problems? Well, of course, we have tons of strategies we can do. Some of the essential and basic techniques to try in these types of questions. Idea number one is to try to guess what's this point. Maybe it's like some famous point, just like here we found that I is the end center. So maybe this point is a famous point, and if we can't find it, then we just need to show that this point lies on the line P, for example, T, and that will be it. Okay, this is one strategy. Another strategy, like how do we show three concurrent lines? There is like this CVA's theorem. We didn't actually discuss it yet. We're going to discuss it in chapter 3. So in the next video, hopefully. However, the main challenge here for CVA, if you know it already, is that we don't have actually a triangle and CVNs. It's not really that obvious here that we have something like that. So probably we're going to skip on that. What other techniques do we know? Well, there is one special technique we discussed in this chapter, how to show three lines are concurrent. And that technique is the radical axis, right? We know that if we have three circles and then their three radical axes, they meet at a point, that is the radical center, right? Of course, we already put the condition when we don't have the radical center, that is when the three radical axes are parallel, that means the three centers are collinear. Anyway, so that means we can actually try to search for three circles here, such that these three blue lines are their radical axes. Okay, if we try to give this a shot here, let's try to do that. So PD and QE and RF, we want them to be the radical axes of three circles. How exactly can we pick these circles? Well, if you try to think about it, if you have something like this, and like this maybe, you want these to be, as we said, the radical three radical axes. Actually, the easiest thing you can come up with is maybe if these themselves, they were the circles like this, right? This thing will be the easiest thing ever, because this is already like the radical axis, radical axis, radical axis, so these will meet at a point. So let's try this idea here. Actually, if you look at it, then that means we want to show that P, D, and something, let's pick for example QE, these lie on a circle. So if you look at the order here, P, Q, D, and E. This is cyclic. So if we can show that this thing is cyclic, then by symmetry we can show the other three, and we'll be done actually. Okay, so let's try to do that. So what we'll be doing is we're going to draw P, Q, D, and E. Let's delete that now, and let's join P, Q, and we need to have D as well, and E, and P. If we can show this thing is cyclic, then we'll be done. Alright, let's try to do that. Okay, how exactly can we show that this thing is cyclic? As you know, to show something is cyclic, we probably should go angle chasing. As there are no intersections to consider power of point. We don't have, for example, intersection of diagonals or something like that. So let's try to simply do some angle chasing. One nice thing about this is we already have all the points on the original circumcircle. So probably we can do some manipulations here and there to basically move the angles into the circle, the angles on the circumference. All right, so our plan right now is, let's say you want to show that two opposite angles add up to 180. So if we just pick these and try to do some angle tracing right now, this will be our goal. So let's try to do angle tracing for this and this. Let's start with this. So our angle is what? It's angle QPE. What exactly is this? I liked when dealing with such questions to, especially with angle tracing, to consider some term that's like bad points. So for example, right now what do we have? We have triangle ABC. Okay, this is our reference triangle. We have the contact triangle DEF. Okay, everything is nice. We know everything about DEF and I. However, the bad points here are actually the last points defined, P, Q, and R, right? We don't know that much about them. We do know, of course, but I mean they are the worst points in our diagram. So when we want to do some angle tracing, our goal is to get rid of these bad points. So to find this angle here, as you can see, we have point Q, point P, and E. E is good, but Q and P are bad. So one technique I try to do is I try to, like when having two bad points in one angle, I try to separate them. Like maybe to turn this into two angles, each angle has only one bad point. This is like easier to handle, one bad point at a time, than handling two bad points at the same time. So using this strategy, okay, instead of working with QPE, let's see what can we do. For example, here, one manipulation is, remember, point P lies on the circumference of the original circumcircle. So we can easily escape to this. If we join PA, now we can say this angle here is the whole angle minus this angle. Now let's see how this actually helps us doing our task. So now APQ minus APE. Okay, this thing is good. It has only one bad point, which is P. This thing, it seems that it still has two bad points, which is like not good. However, actually, if you look at it, this thing doesn't have two bad points, because if you look at it, this is one angle on the circumference. So this angle actually is opposite to what arc on the circumcircle? To arc AQ. So in fact, this point P is nothing, like it's not doing anything. We can replace point P with any point on the circle. For example, we can replace it with point B. And hence, actually, this thing has only one bad point, that is Q. So everything is nice. This seems a nice idea. Okay, right now, the angle APE actually, if you look at it, APE, this thing, we can find the exact angle. We can actually trace this angle. It's very simple. Remember, the main definition for point P, it lies on this circle. And APE is just what? It's actually the, corresponding to this arc, AE. So we can actually, instead of finding APE, we can move it to AFE. And AFE is very easy. It's just 180 minus A, all of that over 2. So it's just 90 minus A over 2. So this angle is just 90 minus A over 2. One thing, when dealing with these 90 minus A over 2, you can either keep it as 90 minus A over 2, or you can write it as B over 2 plus C over 2. Okay, it isn't that big deal. Anyway, so this thing, we know how to deal with it. Now what about APQ? Remember, our goal is to get rid of this bad point P. We can easily do that by moving to another, picking another point. For example, here the best point is to try to move it to angle P, because we want to get closer to this blue angle here. So let's just do that. So this thing right now, it's equal to APQ minus 90 minus A over 2. Nice. So now, can delete these. we got rid of point P totally. Now we're just working with point Q, which is very good. So let me draw now ABQ. That means it's just like this angle here. We're working with this angle right now. This minus 90 minus a over 2, we need to show that it's supplementary to this. So they add up to 180. Okay, how can we handle this? Well, if you look here, remember the definition of Q, it lies on this circle here. And we have point I already there. So what we can do here is like something very simple. One idea we can do is look at point I. If we join BI, you know that this is B over 2 and this is B over 2. And what we're working with is we're working with all of this angle minus 90 minus A over 2. Remember 90 minus A over 2, it's B over 2 plus C over 2. So we're subtracting like ABQ minus B over 2 plus C over 2. So that means this thing here is already B over 2. So this minus B over 2 is already actually something nice. It's just the angle IBQ minus C over 2. Okay, so now we got rid of this part. As I told you, 90 minus A over 2, it's just B over 2 plus C over 2. You can do this manipulation easily. Okay, let me now delete that. Okay, now we're working here with this angle here. IBQ minus C over 2 plus this angle here. Alright, now it's time to work with this angle. How can we handle this angle? Let's have a look at this angle here. Of course, our goal, remember, to show that this thing, if we add that angle, QDE, it's going to get like 180, basically. Alright. Now, actually, one thing you can think about it is if you drop this thing here, this thing is cyclic. Remember, our goal is to show that this thing plus something minus C, of course, it's equal to 180. But we already know that this thing here plus this thing is 180. So that means we just need to show that IDQ is equal to QDE minus C over 2. This is what we really need to do. And of course, if you look at it, it's really not difficult at all, because IDQ, it's actually all of this QDE minus this here, tiny bit. Okay, but this IDE, in fact, it's easily C over 2, because if you look at this circle here, IDE is just the same as C, like ICE, for example, which is C over 2. So yeah, that works actually. And hence, we've just shown that our quadrilateral is cyclic, and similarly, we can show the other two are cyclic, and hence, because the three radical axes, like they're all meet at a point, like we're done basically. Yeah, that's it basically. Alright, as a summary, in this video, we wrapped up the chapter 2 about circles. In this chapter, if you remember, we learned about power of points, we learned about radical axes, radical centers. We also learned about coaxial circles and these kinds of stuff. Finally, we learned about the like if you have an S circle and an X circle, how do we find all of these lengths, the S minus A and S minus B and this stuff. Okay, so let's do a quick recap for the questions we solved. The first question, the idea was really simple. We immediately applied the theorem that we learned, since we have 2 points on this circle, 2 points on that circle. However, we always need to pay attention, because we have a special case if the like O3 was collinear with O1 and O2. So we always need to be careful, otherwise we would have like lost many points here. Of course, here the idea was we caught the radical, the orthocenter, and that of course comes from the simple fact that the radical axis is perpendicular to the line joining the centers. We also discussed the other special case, and the other special case was very easily handled using some length tracing by Pythagoras. Of course, we always think about Pythagoras when having tans of 90 degrees. Alright, for example 2, the Euler theorem. In this question, we simply tried to play with the equation and moved it to a power of point. We translated it to a power of point I, and then we just did some construction. All the construction was logical. It was all based on how we want to handle the question. So we want to have power of point, we draw AI. We want to handle the the similarity. We want to have another triangle such that we visualize everything that we have in the question. So we simply did all of that. We just draw the point E, and everything was simple. The similarity was direct. For the third example, this question was weird as it has everything related to lengths and numeric values. Of course, our idea was we want to get rid of these numeric values. We easily did that by introducing the parameter. How do we visualize it? Using S, of course. And to visualize S, we just need to draw the X circle here, and everything followed smoothly. One very nice idea also here was the idea of introducing the phantom point. Sorry, not the phantom point, I mean here the circle with radius 0. So the circle with radius 0 at A, this was a very challenging idea here. But remember always to keep this diagram in your mind. This will always help you not miss circles with radius 0. Alright, our final example was the Canadian question. So this question, the first part is really a piece of cake. The second part is the challenging one. The idea was simple. How do we show three lines are concurrent? We thought of many ideas, but we picked the idea we learned in this lesson. That is, we want to have three circles such that these three lines are the radical axes of these. And we easily thought about the simplest, basically three cyclic quadrilaterals. We focused on one of them and we did some angle chasing. The angle chasing, however, here was a little challenging, but using our strategy of deleting bad points really helped us. So here we said that we have two bad points. We want to get rid of them, the two bad points. We want to have one bad point at a time. We simply used the idea that point B lies on the circumference of the circle, ABC. So we easily separated them. And then we continued step by step. We got rid of the bad point B. We already now focusing on Q. And everything followed directly. Alright, so we're finally done with chapter 2. And in the next video, we'll be starting with chapter 3 about lengths and ratios. I hope you guys enjoyed the video. Please share it with your friends who are preparing for Math Olympiad as well. And don't forget to like, share, and subscribe to my channel. And join the Discord server as well. And see you guys in the next video.